Hello, good people. How are you? And welcome back to MedZone African Motives. We are still on our grade 10 physical sciences. We are still on our grade 10 physical sciences for term 1. So we are looking into the topics that is waves, sound, and light. So we have already discussed about pulses. We defined what a pulse is and the types of pulses, how they propagate, and then we looked into the principle of superposition, where we discussed about constructive interference and destructive interference. And then we went on to define waves. And then we classified our waves into mechanical waves as well as electromagnetic waves. And we have described different types of um, mechanical waves, where we looked into transverse waves, where we gave an example of water waves. And then we went on to longitudinal waves, where we also gave an example of sound waves. After that, we looked into the key features and the characteristics of each and every type of mechanical waves. And then we closed by looking into the most important type of mechanical waves, which we refer to as sound. And then we looked into its practical application into our daily lives. Why is it that we mostly focus on sound waves when we look into mechanical waves? And then today, I want us to continue and conclude our term 1 topic, which is electromagnetic waves. So today we are going to define what electromagnetic waves are. We are going to see how they propagate, and we are actually going to classify them as either as transverse or else as longitudinal. And then we are going to see different examples of electromagnetic waves and actually get to classify and define how useful and applicable are these waves in our daily lives. So I want us to actually get started with defining what are electromagnetic waves. So we have seen that what we refer to as waves is something that would actually have a wavelength as well as frequency, meaning to say that there is some propagation or else traveling. So when it comes to electromagnetic waves, we define these waves as a type of waves that are made up of vibrating electrical and magnetic fields. So electrical magnetic waves, these are generated by accelerating an electric charge. So we can actually get to see that electromagnetic waves, they are produced whenever electric charges vibrate or else they accelerate. Whenever they vibrate or they accelerate, then we know that we would have what? A resultant of what? Of electromagnetic waves. So how exactly are they generated or else are they produced? So what happens is we might start with a vibrating electrical charge. For example, let's take for example an electron that moves back and forth or else up and down. The electric charge is actually causing what we call a change in electric field. So whenever we've got a vibrating electric charge, it produces a changing electric field. And we know that wherever there is a changing electric field, there is production of a changing magnetic field. That is how electric fields and magnetic fields they get to interact. Whenever either of one is changing, it produces the other. So we are saying that we would initially we will be having an electric charge that we can take an example of an electron. We know that an electron is negatively charged. So by having an electron, this electron, when it actually gets to vibrate back and forth, what it is actually doing is it is changing the electric field, which is the region in which you can actually get to feel the electric field force. Once there is change in electric field, there will be change in the magnetic field. And once there is continuous change in electric field and magnetic field, then we have got an electromagnetic wave propagating. And we would know that these waves, they do not require any medium. They can propagate anywhere, in a vacuum, in air. They do not require any particles for them to move. All they need is to have an electric charge vibrating so that it can be accelerated by change in electric field as well as change in what? In magnetic field. So this is an interaction of a change in electric field and change in what? In magnetic field. So you would actually get to see that at the end of the day, we can simply say that electromagnetic waves are formed by the movement of electric fields and magnetic fields. And electric fields, when they move, they actually get to create a change in magnetic fields. When magnetic field moves, they also get to create a change in what? In electric field, which later therefore accelerate an electric charge, thus generating what? An electromagnetic wave. So that is how, or else simply how, we can explain what we refer to as what? As an electromagnetic wave. So some, they would actually get to ask themselves, so how do they move or travel or propagate, since you are saying that they do not require either a medium or else particles for them to move? So we are saying that these waves, they do not need particles. They can travel either in a vacuum, in air, water, or else in space. So how they travel, it is due to the change in electric field that produces magnetic field. And this change in magnetic field is the one that produces what? Another change in electric field. And these two fields move together at right angles. Whenever there is change in the electric field, it causes a change in magnetic field. Whenever there is a change in magnetic field, it will also cause a change in electric field. Whenever there is that change in electric field, it will cause a change in what? In magnetic field. So from this diagram that I brought here, I'm sure you can actually get to follow through what we are saying. For example, we are saying that this is an electric field. And when there is an electric charge that is moving back and forth, it will actually get to cause a change in the magnetic field, so that the magnetic field would actually get to move what? Up and down. And this change in magnetic field, which is causing up and down, if our electric field was in the positive direction, it will now cause this electric field to change to be in the negative direction. Meaning to say that if it was vibrating going forth, it will now vibrate going backward. So we are just creating changes in the what? In the two fields. And these changes in the two fields, they actually move together at right angles. So you would be having this moving up, whilst this is moving what? Perpendicular to this direction. So they move together at right angles to each other. And they also move at a right angle towards the propagation of the what? Towards the propagation of the wave that they are creating. So we will therefore call these ones what? Transverse waves. Why? Because the particles, or else let's get to say that whatsoever is causing the wave is actually in the direction that is perpendicular to the propagation of the what? Of the wave. Just like when we talked about mechanical waves, we said when it comes to transverse waves, the particles of the medium are the ones that are actually what? Displaced perpendicular to the what? To the direction of the what? Of the wave. So the wave will be going to the right, whilst the particles are displaced either what? Up, or else they can be displaced either what? Down. That is actually what is happening here, where we are saying that now, instead of us having particles that are actually what? That are actually being displaced, whatsoever is happening is we are having what? An electric charge that is being accelerated. So the direction of acceleration is what we are referring to as in the perpendicular direction to the wave that it is creating. So you would have to see that you would be having a wave that is going forward, whilst the electric field is actually what? In the perpendicular what? In the perpendicular direction, the electric charge. So from this, since we have classified these as what? As transverse waves, we would actually get to see that they have what we call crest and they have what we call troughs. And this will lead to them having what we refer to as a what? As a wavelength, which is the distance in between one complete wave, which is to say the distance between two consecutive what? Crests or troughs. So now let's look at the key features of electromagnetic waves. We now know how these waves are generated. They are just generated by what? By accelerating charge. They are generated by accelerating charge, or else by what? By vibrating charge. Whenever there is vibrations within charges, where electric charges they get to vibrate, then we know that electromagnetic waves are produced. So electromagnetic waves are simply produced by vibrating electric charges, or else by accelerating what? Electric charges. And then how do they get to what? How do they get to travel? We say that they travel perpendicular to the direction of the what? Of the wave. To say that the electric charges, these are our electric charges, and this is the direction of our wave. So as the electric charges they vibrate up and down, the wave that is produced is going what? It is moving in a horizontal direction, which is in a horizontal plane, which makes a 90-degree angle to the what? To the direction of the wave. Hence, therefore, we call this a what? A transverse wave. So we are saying that electromagnetic waves, they are simply transverse waves. And then we are saying that they are produced due to electric and magnetic fields vibrating at right angles to the direction of what? Of motion. Hence, therefore, they've got crests and they've got troughs. We can see that here we have got a crest on our electric field, and then we have got a trough. So the distance in between two consecutive crests, we call that a wavelength. So that is our wavelength. Or else I would have used this trough of the magnetic field as well as this crest of the magnetic field. The distance in between these becomes our wavelength. And then we know that as long as we have got a wavelength, which is the distance that is traveled by one wave, then we can know the time that it will take to cover that distance, which we refer to as the period. And then once we know the period, we can certainly know our frequency, because we know that frequency becomes the number of waves that passes through per unit 1 second, or else frequency can be given by 1 over time period. Once we have our frequency, our time period, and our wavelength, then we can simply know the speed, which is how fast these waves that are being produced are traveling. But however, we need to know that in a vacuum, all electromagnetic waves, they travel at the speed of light. And we know that light travels at a speed of 3 times 10 to the power 8 meters per second. So from the wave equation, which is the general wave equation of all waves, we know that the speed of any wave is given by its frequency and the wavelength of the what? Of the wave. So we are saying that this speed, if it was sound waves, it was going to be 340 meters per second, an approximate of that, if it was sound waves. Now we are now saying that when it comes to what we refer to as electromagnetic waves, the speed of electromagnetic waves in a vacuum becomes the speed of light. So electromagnetic waves, they move at a speed of light in a what? When it comes to in a vacuum. That being said, this is the speed of light. So whenever we are dealing with electromagnetic waves, we should know that the speed that we should consider is that of the speed of light. And then we can simply know our frequency if we know the wavelength of the what? Of the wave. Or else, if we know the wavelength, we can simply know our frequency. And these pictures that I'm showing here on these slides, I just took them from the internet. I just wanted them to serve as a clear picture or depiction of how these waves they actually get to propagate, as well as how you can identify their key features. For example, here we can see that from this diagram we can be able to determine the wavelength of what? Of electromagnetic waves. And also from this diagram, they've actually shown for us that this is the direction in which our electric field would be moving, or else would be vibrating in, or else along. And then this is the direction in which our magnetic field would be changing. And then this is the direction of our what? Of our wave. That shows you that the waves or else the wave is in perpendicular direction to the what? To whatsoever that is creating it. They exist 90-degree angle here, 90-degree angle there. That's why we call these transverse waves. So you should know that electromagnetic waves, they are what? They are transverse waves. And you should know why. Because we are saying electric and magnetic fields, they vibrate perpendicular or else at right angles to the direction of what? Of motion. And there exist crests as well as troughs, so that we can actually get to determine our wavelength in regards to what? To the distance in between two consecutive crests or two consecutive troughs. After we've said that, there is one important characteristics or else characteristic of electromagnetic wave. That is what we call its dual nature. What is it that we are saying? If you look, for example, the most common example of electromagnetic radiation that we can think of is what we refer to as visible light, the light that we use for our vision. I'm sure if you actually get to take a mirror and then you actually get to show it, or else let's get to say you actually get to present your mirror in such a way that it faces the direction in which your light is coming from, the light that comes from the sun, you can see that at some point in time the light can be reflected, so that you can now start directing that reflected light that is on the mirror. And also, you know that whenever we have got a tree, let's say the light is actually, maybe it's during the day. You know, during the day sometimes it can become hot in such a way that you can wish to just get to what? To sit down under a shade, either it's shade of a tree or a building. That shade, it shows that our light at some point in time it is reflected, at some point in time it is diffracted, or else we can say that that building will show some barrier which is resembling what we call interference, diffraction, reflection, and refraction. So we are saying that from our visible light, we can know that light can bend when passing through a prism, and then also it can create interference patterns, which is the shadows that are the ones where you get to say that let me just get to sit down the shadow of a tree, maybe it will be warmer there. So those the shadow that you are following is what we call interference patterns. So in summary, we are saying light exhibits wave-like properties, or else it behaves as a wave in such a way that it can be what? It can be diffracted, or else there can be interference, or else there can be reflection or rarefaction or refraction. Additionally, light can also behave like a stream of particles called photons. What do we mean by that? We are saying that light can actually come as particles that are carrying energy. I'm sure from the example that I've given you of you trying to sit down under a shade of a tree. Why does it become cooler under the shade of the tree? It's because we are saying that the particles or else the photons that are being carried by that light are now being reflected, or else they are now being what interfered with. They are no longer reaching to where you are. So that's where we are saying light can also behave like a stream of particles, where if you actually get to present a barrier, those particles will not be able to pass through. So let's use this diagram to actually get to follow through what we are saying. We are saying that light at some point in time, it can actually be interfered with, meaning to say that it can actually behave like a wave, which is to say there is some interference. And then we are saying that whenever we present a barrier, there can be a shadow of this light. And then within the shadow of this light, we are saying that the particles, they produce what you call straight shadows, which shows that waves, they've actually bent into a shadow. So the light waves have bent into a what? Into a shadow. So that's a behavior of a wave. And then when our light is actually what? Is actually maybe presented through a barrier, I would actually see that some photons of energy will not get to reach through under that shade. That's why it is cooler under the what? Under the shade, and then it is hot where the light is actually hitting direct. So we are saying that light can also behave like a stream of what? Of particles called photons, which carry energy. That is the reason why you would actually get to say the light that is coming from the sun is actually hot during the day. So that is the what? The particle like nature. So you have seen that this phenomena is what we refer to as the dual nature of what? Electromagnetic waves. Meaning that these waves, they behave both as either a wave as well as either a particle. When they behave as a wave, they move as transverse wave with wavelength and frequency. And then when they behave as particles, they are made up of individual bundles of energy, or else photons. So that is what we call the dual nature of electromagnetic waves. So when it comes to your exams, they would actually get to ask you to say, define the dual nature of electromagnetic waves, or else describe the dual nature of electromagnetic waves. You simply say that uh, the dual nature of electromagnetic waves, it actually tells us that electromagnetic waves, they can either behave as a wave where they move as transverse wave with wavelength and frequency, and as well as a particle where they are made up of individual bundles of energy, or photons. That is what the dual nature of electromagnetic waves mean, or else states. Now, since we now know almost everything about electromagnetic waves, from the example that you have given, to say that the most common example of electromagnetic waves is what we call visible light. But the light that we can see, which is visible electromagnetic radiation, is only part of all the electromagnetic radiation that exists. And the full electromagnetic radiation is what we refer to as the electromagnetic spectrum, which is to say that it is an arrangement of electromagnetic waves in accordance to the highest frequency to the lowest frequency, or else to the from the longest wavelength to the shortest wavelength. So this is what we refer to as the electromagnetic spectrum. This is the full description of what we refer to as the what? Electromagnetic radiation spectrum, where we have all the what? Individual examples of electromagnetic what? Waves. So on this electromagnetic spectrum, you will see that we start from the radio waves, where we know that radio waves, they have got the what? The longest wavelength. They have got the longest wavelength. And then, having a longest wavelength, you would know that you would be having the what? You would be having the lowest what? The lowest frequency. You would be having the lowest frequency. And then as we move from radio waves, microwaves, infrared, visible light, and then ultraviolet rays, X-rays, and gamma rays, we are actually what? We are actually increasing the frequency, whilst the wavelength is becoming what? Short. So here we've got the shortest wavelength and then the highest frequency. So you need to actually get to know how to arrange the electromagnetic spectrum in accordance to the lowest frequency to the highest frequency, or else from the longest wavelength to the shortest wavelength. So the shorter the wavelength, the higher the frequency, and the higher the penetrating energy, or else the higher the energy that it carries. And then the longer the wavelength, the lower the frequency and the lower the energy that it carries. So that is what we refer to as the what? As the electromagnetic what? Electromagnetic spectrum. So we actually what? We actually need to be able to understand as well as explain and actually what? Arrange these in accordance to their what? To their increase in frequency and decrease in what? In wavelength. After we now know that, we need to know what are the applications and what are the uses of electromagnetic waves in our daily lives. Why is it important for us to be studying this electromagnetic spectrum? What does it tell us, and how can we be able to make use of it? How can we be able to make use of the knowledge that we have in regard to the what? To the electromagnetic what? Waves, as well as the electromagnetic spectrum. So this is the reason why. So the uses of these electromagnetic waves and their applications are, for example, we know that one, for radio waves, they are used for TV broadcasting, for our cell phone communications, and then for what we refer to as Wi-Fi, which is wireless fidelity. And then they can also be made use in actually what? In manufacturing what we refer to as Bluetooth devices, like our speakers, our telephones, or else all our Bluetooth devices. That includes maybe remote controls that we use through what? Through Bluetooth. We make use of radio waves to actually get to manufacture and design these devices. And then when it comes to microwaves, we know that microwaves are used in ovens, which is used for heating food. And then they are used in satellite communication. They are also used for radar systems, which is, you see those police speed guns, those speed guns which monitor the what? The overspeeding, or else the speed of different what? Motor vehicles, as well as what? Weather radars, which is to say in monitoring our weather forecast, we make use of what? Of microwaves. And then when it comes to infrared radiation, this is usually used either in TV remote controls. I'm sure you've seen that when you actually get to press a TV remote control, you would actually get to start seeing either a red or blue or green light that is actually being shining from the what? From the remote control. That is what we call infrared radiation. That is why you need to sort of position your TV remote control towards either the decoder or else the TV itself. If you don't get to show it upon that, it would actually not respond. What we are doing is we are directing our TV remote control to the sensor of our infrared radiation. So that is where we apply our what? Our infrared. So we have TV remote controls, we have got heat lamps, we have got night vision cameras, as well as thermal imaging. And then when it comes to visible light, we all know that Without visible light, it will be difficult for us to actually get to see. I'm sure you can actually get to understand if we say, let's say, for example, it is during the night and you are in your room, and then maybe electricity just gets to cut off, or else your light switches off. I'm sure when you are in the dark, you get some challenges or else some troubles in what, in locating or else in seeing things. So we use visible light for human vision or else for vision. And then we also use visible light for our cameras, our lamps, torches, as well as photosynthesis in plants. That is where we use what? Visible light. And then after visible light, we have what we refer to as ultraviolet light or ultraviolet radiation. This is used for sterilization or else for sterilizing medical equipment. When we say sterilizing medical equipment, what we simply mean is for killing germs or else for killing what? Microorganisms, for killing undesirable microorganisms. That is what we refer to as germs. Once we kill these, we have sterilized our medical equipment. Hence, therefore, there won't be any spread of these disease causing organisms. And then we can also use it for tanning. But however, mind you that when it comes to tanning, this can also get what? To damage our skin. We can also get to use it for detecting forged banknotes. We can use it for vitamin D production in skin. So, especially when it comes to pregnant women, they are usually recommended to go and actually sit or else bask in the sun. Whatsoever that they are doing is they are trying to harness what we call ultraviolet radiation. This gives vitamin D in what, in our skin. And then we can actually get to use it for what? For detecting forged notes. That is what they use either in banks or else in security what? In security features. When it comes to either maybe on the tailor or else on the shops. Now, X-rays. X-rays, they can be used for medical imaging, which is to actually get to what? For imaging of broken bones, fractured bones. I'm sure you've heard many people who would get to fracture their bones or who gets to actually have broken bones. They actually get to tell you that I went for what? For an X-ray. What they mean is they went for a medical imaging that was using what? X-rays. And then we have got airport security scanners. Airport security scanners, they also use X-rays. And then we have got quality control in engineering. We can use our X-rays in quality control in engineering. That is to detect where there are fractures when it comes to our what? Our metal equipments that we would have used in designing different what? Engineering what? Equipments. And then we now lastly have what we refer to as gamma rays. These are used for cancer treatment or else radiotherapy. This is due to their what? To their high penetrating energy or else to their high radiation. They can actually get to kill these cancerous cells. They are also used for sterilizing food and medical equipment as well, since they also carry high what? High radiation like ultraviolet. They can be used for sterilizing. They can be used for detecting cracks in metals as well. So these are examples and uses as well as applications of what? Of electromagnetic waves. So, in summary, we have actually looked into what we refer to as what? As electromagnetic waves, where we have actually described electromagnetic waves. We have described electromagnetic waves in a way where we say that these are waves. Let me just get to say these are waves that we have described by using the above given definition, where we say that they are waves that are made up of vibrating electric and magnetic fields that move through what? Through space. So wherever electric charges vibrate or else they are accelerated, we generate what? Electromagnetic waves. If that is the case, then how do we get to apply electromagnetic what? Electromagnetic waves in our lives? We have described the uses and applications of what? Of electromagnetic waves. Where we have said radio waves, you actually get to use them in what? TV broadcasting, cell phone telecommunications, and then microwaves in your microwave ovens, as well as in radar systems, infrared radiation for TV remote controls, visible light for human vision and cameras, ultraviolet radiation for sterilization and tanning, as well as detecting forged banknotes, x-rays for medical imaging. And then we lastly come to what? Gamma rays for cancer treatment. So that is that about electromagnetic waves. So this marks the conclusion of waves, sound, and light. So that is what they expect you to know when it comes to grade 10, term 1. So let's meet in our next video where we actually get to start attempting some questions that has to do with what? With these topics, or else that is to do with pulses, waves, sound waves, as well as electromagnetic waves.